Hello, I'm Martin. Together with James, Aidan, and John, we're going to navigate our way through hypersonic boundary layers. During this podcast, we will explore macroregimes and what they are. We will then move on to boundary layers, covering the basics of boundary layers. From there, we will look at viscous interactions that occur due to the high Mach numbers involved. We will then move on to shockwave boundary layer interactions experienced at hypersonic flow. Intakes will also briefly be investigated, including design considerations required due to the thick boundary layers. To finish up, we will look at some example hypersonic vehicles and how the hypersonic boundary layer characteristics have influenced their designs. Before delving into the various Mach regimes, an understanding of what Mach number is important. The Mach number is obtained by the equation shown. In this equation, U represents the velocity of the body being considered. Gamma is the ratio of specific heats. R is the molar gas constant, and T is the temperature in Kelvin. At the bottom of the scale is subsonic flow. The majority of what we experience in everyday life is subsonic. This region considers flow below around Mach 0.8. On the other side of m equals 1, we have supersonic flow. This involves flow between around Mach 1.2 and Mach 5. The region between Mach 0.8 and Mach 1.2 is called the transonic region. In this region, localized areas may experience subsonic flow, whilst others may be in a supersonic flow regime. In this region of flow, local shocks and mini-shocks may be observed. Hypersonic flow considers any flow greater than Mach equals 5. It is sometimes divided into hypersonic flow, which is to around Mach equals 10, and high hypersonic flow, which represents Mach regimes higher than this. At the upper end of the scale, we have re-entry vehicles. This podcast focuses on the hypersonic flow regime and the boundary layer characteristics associated with it.
As Martin briefly discussed, hypersonic flow is Mach numbers between Mach 5 and Mach 10. However, it is to be noted that this is debatable among the aerodynamics profession. This is because the jump from supersonic to hypersonic isn't as clear-cut as breaking a sound wire, especially with no hypersonic boom observed, but the general agreement is at Mach 5. As the body's Mach number increases, the density behind the shockwave generated by the body also increases, and this corresponds to the decrease in volume behind the shockwave due to the conservation of mass. Consequently, the distance between the shockwave and the body decreases at higher Mach numbers. Further increasing the Mach number will result in higher temperatures being generated in the region behind the shockwave and the body, also known as a shock layer. At Mach numbers above Mach 5, the shock layer becomes so thin that interactions occur between the shockwave and the viscous boundary layer on the surface. Chemical reactions take place in the air, with oxygen and nitrogen molecules associating, or to put this in other terms, molecules are physically torn apart. When the Mach number is sufficiently large enough, such that viscous interaction effects begin to dominate the flow field is called hypersonic. Research into hypersonic aerodynamics began around the time of the Cold War era due to a rapid investment into missiles and other high-speed vehicles. In the post-Cold War era, between 1985 and 1995, the concept of air-breathing supersonic combustion ramjet-powered trans-atmospheric vehicles to provide a single-stage propulsion system into orbit capability was researched. Today, focus has shifted to the possibility of hypersonic transportation. One of the most recent hypersonic vehicles that made aeronautical history is the X-43 HyperX, which achieved sustained flight for 11 seconds at Mach 10. A scale model is shown in the image during hypersonic wind tunnel testing. Plasma effects around the body are clear due to intense aerodynamic heating effect. In particular, hypersonic viscous interaction is an important area of modern hypersonic research, along with the issues involved in preventing high Reynolds numbers and its associated turbulent flow, which Aidan will explore in more detail. Stability and control of hypersonic aircraft is also challenging at the current level of development. The Mach number changes rapidly and significantly during hypersonic flight tests, which means that any maneuver must be executed efficiently in all axes over a very short time period. Also, as the Mach number increases, the lift-to-drag ratio decreases as shown in the graph. This further promotes inefficiencies in the design. Future designs could come up with new solutions to counter this problem.
A boundary layer is the layer of fluid in the immediate vicinity of a body's surface where the effects of viscosity are significant. In the boundary layer, the velocity at the surface is zero, assuming the no-slip condition, and this increases to essentially the free stream velocity at the outer edge of the boundary layer. The velocity gradient is quite steep near the surface of the boundary layer and slowly decreases in a perpendicular direction to the surface. The thickness of the boundary layer is normally defined as the distance from the solid body to the point where the viscous flow velocity is 99% of the free stream velocity. The Reynolds number of the flow increases as you move downstream. This leads to flow progressing from laminar to turbulent flow downstream. Hypersonic vehicles fly at high altitudes where air has a low density. Hypersonic flight will also lead to significant heating in the external air due to viscous effects. Since the pressure gradient normal to the flow within a boundary layer is approximately zero for low to moderate hypersonic Mach numbers, the increase of temperature through the boundary layer coincides with a decrease in density and also with an increased viscosity due to viscosity increasing with temperature. This low density due to the high altitude and high temperature, as well as the high viscosity present, leads to a low Reynolds number for the flow. As boundary layer thickness is proportional to the inverse of the square root of Reynolds number, the boundary layer for hypersonic flow will be quite thick. The low Reynolds number will also lead to a larger laminar region in the boundary layer. The less turbulent and thicker boundary layer will serve to decrease aerodynamic heating of the body due to less convection as a result of less turbulence present and the thicker boundary layers which tend to have less heating associated with them. However, the heating involved due to the viscous effects are still extremely large, and because of this, vehicles have to be designed accordingly. Thickness increases rapidly with Mach number. The approximate proportionality between boundary layer thickness and Mach number squared will further increase the thickness of the boundary layer due to the high Mach numbers involved in hypersonic flow. Temperatures within the boundary layer increase rapidly. The increase in temperature also decreases the density of the air in the boundary layer, and the especially hot air near the body's surface. This especially hot air near the body surface serves to expand the area of the boundary layer near the surface. These lead to boundary layers of the same order of magnitude as the shock waves. It is also worth noting that cooling the wall reduces the thickness of the boundary layer, and that both the coefficient of skin friction and Stanton number decrease as Mach number increases, and both can be increased by cooling the wall. Shockwave angle decreases with increasing Mach number, and this means that the wave will be closer to the boundary layer, further increasing interactions between the inviscid flow behind the shockwave and the viscous flow in the boundary layer. The shock layer becomes highly viscous, which affects the shape of the shockwave and the surface pressure distribution. This results in high pressure differences between the leading edge and areas downstream. This results in increased aerodynamic heating at the leading edge. The differences in temperature between the leading edge and areas downstream pose significant design challenges for hypersonic vehicles. Distinct from the viscous interactions between the viscous shockwave and the boundary layer, there are also interactions due to impinging shock waves caused by external bodies to the surface. The incident shock waves causes separation of the boundary layer due to the severe adverse pressure gradient across the shock wave. This separation occurs slightly upstream of the shock wave due to the subsonic region of the boundary layer allowing the pressure to travel upstream. The separated boundary layer induces another shock wave called the induced separation shock wave. The separated boundary layer turns back towards the body and eventually reattaches to the body. This creates another shock wave called the reattachment shock wave. At the point of reattachment, the pressure is high and the boundary layer is quite thin. This leads to a significant amount of localized heating occurring at the reattachment point. This potential localized heating and the damage that this could cause makes the understanding of these interactions fundamental for the design of hypersonic aircraft.
Hypersonic boundary layers are key to the design of hypersonic engines. The engine that is currently being considered for powering proposed hypersonic planes is the scramjet, which stands for supersonically combusting ramjet, where a ramjet is an engine in which the air is compressed by a specially designed intake and the velocity of the oncoming flow. There are no moving parts in a ramjet compressor. A scramjet is effective only in supersonic airflow, meaning the engine will only start when already flying at supersonic speeds. As the air enters the intake, it is compressed, and this does two things. It slows the air to a speed at which the fuel can be more easily mixed into the flow, and it increases the pressure and temperature enough to ignite the fuel. This causes the air to expand and provides thrust. Boundary layers are key to the design of scramjet intakes, as the supersonic air causes an adverse pressure gradient, thickening the boundary layer on the engine's surface. This reduces the amount of air that can be efficiently expanded to provide thrust. If the boundary layer grows too thick, it will separate and stall the engine. At hypersonic speeds, this is not advised.
At such high speeds, aerodynamic heating becomes a major problem. Consequently, the structure has to be fabricated from special high temperature materials. Research investigated in this area identified nickel titanium as a skin cover and small wings to reduce aerodynamic drag, such as the Boeing X-51.
On the other hand, re-entry vehicles are equipped with heat shields that serve to both protect the vessel from the enormous temperature and to provide enough drag to slow the craft down. Ablative heat shields are made of a material that is designed to reduce temperature by constantly evaporating, producing a cooling boundary layer of gas that keeps the highest region of temperature away from the surface of the vessel and carries heat around and away from the shield.
In summary, the need to study and better understand hypersonic flow stem from our desire to go faster and push the bounds of what is possible. It is particularly important to consider how the boundary layer is affected due to high Mach numbers and how the boundary layer interacts with characteristics associated with hypersonic flow. Researchers and the aerospace profession as a whole have to rethink the design process when considering hypersonic flow, with careful consideration required in order to use the boundary layer as an advantage along with exotic materials in order to ensure the vehicle can cope with the high temperatures experienced, with scramjets appearing to be the most viable form of propulsion. I would like to take this time to say thanks and hope that your knowledge of hypersonic boundary layers has improved through this podcast.